The last big theorem we're going to see in this class is the divergence theorem. And the divergence theorem is a generalization of Stokes' theorem to 3 dimensions. So in Stokes, we related a line integral to a surface integral, and the divergence theorem relates a surface integral to a 3-dimensional integral, so an integral of volume. Okay? This was a theorem that was discovered by Gauss, by Carl Friedrich Gauss, but it was also discovered in Eastern Europe by Ostogradsky. So sometimes it's called Ostogradsky's theorem, or Gauss's theorem, Ostogradsky-Gauss's theorem, or just the divergence theorem. So this is what the theorem says, again, with the usual qualifications that make these 2 integrals be the same. Just as a reminder, what is the divergence? The divergence is, remember that a good way to remember is the divergence is the gradient dot product with the vector field. Much easier than the curl. The curl is the gradient cross product with the vector field. The divergence is just the dot product with the vector field. So this function right here is just one function. It's a scalar function, and we're integrating a scalar function with respect to volume. Okay? So let me find some integrals. So we're going to do the total flux of the vector field F over the unit sphere. So what does that mean? What we're trying to figure out is the total flux. So the flux integral was the integral over, if the sphere is S, is the integral of F ds. Okay? And what they tell me is that, well, what the divergence theorem tells me is that I can actually replace this. So if this is the sphere of radius 1 is, again, just like this. Here's the sphere. I don't know how to draw a solid ball, but the volume, or I don't know how to make it be solid. So the solid ball of radius 1 instead, I can replace the integral over the surface by an integral in volume of the entire ball of radius 1 of the divergence of the vector field d volume. So that's what we're going to do. Instead of doing an integral over the entire surface, which I would have to do a parameterization. I have here the parameterization just in case. I can parameterize the sphere and do an integral over that entire sphere of a vector field. I would rather not do that. That was a complicated formula. Remember that it had to be F evaluated at the parameterization times the cross product of the parameterization of the dot, the normal vector. So there was a lot to do in there. So instead of doing that, I'm just going to do an integral of the divergence. So F is x squared, 0, 0. So what is the divergence of F? Will be the derivative of the first coordinate with respect to x, so that's 2x, plus the derivative of the second coordinate with respect to y, plus the derivative of the third coordinate with respect to z. So the divergence is just 2x. So then what I have to do, this integral will be the integral over the entire ball of 2x d volume. But now, if you break this ball, you cut it in two. So now I'm going to cut the ball in two. And this is for positive x, and this is for negative x. you see that this integral, so if this is b1 and b2, this integral will be also the integral over b1 of 2x dv plus the integral over b2 of 2x dv. And when x is negative, this is the same as minus the integral over b2 of 2x dv. And this and this will cancel out, and what you get as a result is just 0. This is what's called just using symmetry on the ball. There are just as many points that have positive x as there are negative x. So when I integrate this function, this is an, you remember odd functions in one variable? This is an odd function in the entire ball. Okay, every point that has an x that is positive, there's a corresponding point in the ball that has negative x. So the integral overall of this function 2x will be 0. And one way of showing that is by sort of like breaking it into these two halves of the sphere, where the x is positive and where the x is negative. Okay, so if you go through the entire exercise of parameterizing that ball, then you can show this. How would we parameterize the ball of radius 1? I would do it in spherical coordinates, and that is with radius, so rho up to 1, with theta up to 2 pi, with phi up to pi. And then you can do the entire integral of, of 2, the function was 2x. So you can do the entire integral over the ball of 2x dv in spherical coordinates. Okay? And what you're going to get at the end of the day is that you're going to see that the integral is also 0 by some, there's one of the trigonometric integrals that you get here is just going to be 0. All right? So if you want, this is a good exercise to remind you how to do spherical coordinates. Do that part. Set this integral up as a spherical integral. So let me do a different one. So what about if we do the total flux of the vector field zyx over the unit sphere? So again, I would be integrating over the entire surface f ds. And again, I could just replace by, thanks to Gauss, I can use the divergence. I can use the divergence theorem to replace that integral by the integral of the divergence of f with respect to volume. So I just need to compute the divergence. F is zyx. So the divergence of f will be the derivative of f with respect to, or the derivative of z with respect to x, that's 0. The derivative of y is 1, and the derivative of x is 0. So the divergence is just constant equal to 1. So this will be the integral over the ball of radius 1. So x squared plus y squared plus z squared is less or equal to 1 of 1 dv. But that is precisely the volume of the ball. Remember that the integral of 1 dv is a volume. So this is the volume of the ball, and that is 4/3 pi r cubed. So this is 4 pi thirds. We can again, we could have done it with surface, parameterize this function, parameterize the surface, use the parameterization, evaluate the f at the parameterization, do the dot product with the normal vector of the parameterization, and so on. You can do it in terms of surface, but using the divergence theorem, just by integrating over the entire ball, it turns out to be a lot easier to do. Okay? So it's another one of those switcheroos from one to the other. Let me see if I have some other examples here. So what about if I'm doing the, evaluate the integral of f ds, where f is the vector field, blah. And S is the surface of the region bounded by z equals 1 minus x squared, and the planes z equals 0, y is 0, and y plus z equals 2. I like this exercise because it's going to give us a new chance to interpret this region. So let's see what this region looks like. So what is z equals 1 minus x squared as a surface in space? What I can do is draw it in the xz plane. What is this in the xz plane? It's an upside down parabola, and x equals 0, the height is 1, so it looks like this. Okay? I have to be above the plane z equals 0 and y equals 0, so I'm in the, at least in the first quadrant, yeah, and y equals 0, so I'm in the first quadrant, or in the first octant. And then it has to be above, yeah, above that, and it has to be above, or to the right of this, okay? And that is what that surface is in the xz plane, but since there is no constraint on the y, this just continues like this, so it's something like this. Okay, so it looks like this, like that. And there is no constraints on the x value. And now, what is y plus z equals 2? What does that look like? What I can do is draw it on the yz plane. On the yz plane, this is y is 2 minus z. So that is, what kind of graph is that in the yz plane? That's a line at z equal, or yeah, at z equals, let me maybe graph it as easier to see if I write it as z equals 2 minus y. When y is 2, z is 0, so somewhere here. And when y is 0, z is 2. So it goes like this. And that plane also does not depend on x, so it's a plane like this. So what I do is cut this sort of like top of a parabolic cylinder by this plane, and it's going to look something like this. Okay, so I think that the figure ends up looking like, let me draw it like this. Something like that. Okay, so that is my my surface. And this is the surface of the region bounded by those planes. Great. So now what I want to do is try to integrate over that surface. So I would try to do the integral over the surface of f ds. And that surface has like 1, 2, 3, 4, at least 4 different sides that I would have to parameterize individually to do these surface integrals. So it is much more convenient to switch, thanks to Gauss, use the divergence theorem to switch to an integral over the region bounded by those graphs, and of the divergence of f in volume. So what is this region entirely? You can see now that I can parameterize this by going in x, then in z, and then in y. Okay, I can see that I can go from x, from -1 to 1, then in the xz plane up to this graph, and then in the y coordinate I can go from 0 up to this plane. So that tells me that this I can parameterize as -1 up to 1. the z coordinate goes from 0 up to 1 minus x squared. And then the y coordinate can go anywhere from y up to 2 minus. So that's going to give me the bounds for this triple integral over here. The bounds are going to be given by these bounds. I still need to compute the divergence. So let's look at that. So let me compute the divergence of f. So the divergence is going to be the derivative of the first coordinate with respect to x, that is y, plus the derivative of the second coordinate with respect to y. That's lucky because it does not depend on y, so that is just 2y, plus the derivative of the third coordinate with respect to z. There is no z in here, so that is awesome. That is just 0. So the divergence is actually just the function 3y. So what I'm trying to do, then, the integral over the entire surface. By the way, remember we did that symbol to indicate a closed loop. When you have a closed surface, sometimes people use that, especially physicists, use that double integral and a loop to say that it's the full surface. That is going to be the integral over the region of 3y dv, and that is going to be the integral. X, remember, was going from -1 to 1. The y coordinate is going from, the z coordinate is going up to 1 minus x squared. Let me write it here, that the second parameter is z. And then the integral from 0 to 2 minus x of dy. And the function to integrate is 3y. 2 minus z, yes, thank you. Okay, so we can integrate that. What is the integral from 0 to 2 minus z 3y dy? Well, that is just going to be 3y squared divided by 2 evaluated at 0 and 2 minus z. And that turns out to be 3/2 of 2 minus z squared. I'm going to leave it like that because then the next integral that you do is with respect to z. So I'm going to get the integral. So the next one is -1 to 1 from 0 to 1 minus x squared. And now I'm integrating 3/2 of 2 minus z squared dz dx. The integral of 3/2 2 minus z squared dz, that is -1/2 2 minus z cubed. So what you get here is the integral of -1/2 2 minus z cubed between 0 and 1 minus x squared, which turns out to be, so this is still the integral in dx. It's the integral from -1 to 1 of 4 minus 1/2 1 plus x squared cubed dx. And you can do that integral. This integral turns out to be, the value of this is 184 divided by 35. Okay? So you can do, you can use the divergence theorem to calculate something like that. I think I started writing. This is for the previous problem, not for this problem. This was a different one. For this problem that I had above, you can actually do the same thing. You can figure out what this region is, but what is the divergence of f? The divergence of f will be the derivative of 0 with respect to x, the derivative of y with respect to y, and the derivative of minus z with respect to z is 1 minus 1 equals 0. So if you switch with divergence using the divergence theorem, then you can see that this integral, whatever that surface is, as long as it's some surface that is a closed surface, that will be also 0, because it's the integral over the region of the function 0 in volume. The last thing I wanted to mention about the divergence theorem is that, as you can imagine, we did sort of like Green's theorem, which was changing a line for an area, Stokes' theorem, which was the integral of a curve replaced by a surface, the divergence theorem, which replaced the integral of a surface by the integral of a volume. And the way that Gauss generalized this theorem is to n dimensions. So if you have an n-dimensional object, you can compute, you can replace the concept of surface and the concept of volume by these sort of like hypersurface and hypervolume concepts, and then the same concept or the same theorem holds in dimension n, which is some sort of like surface of the region is equal to the volume, so some volume integral over the inside of that surface. Yeah. Yeah, so this is where all of those, this is the theorem that is used in that. There's all sorts of applications that come up in physics, and some things like Maxwell's laws. They are all mathematically, you can derive them from the divergence theorem. So thank you, everyone.